All right. We are coming down the home stretch here of being able to work with dyes and understand how we can get them to bond on to different things. We are, the last two pieces we have here is we need to understand what we call polarity. We've talked a bit about that when we talked about electronegativity. Remember we said which of these two bonds has a greater dipole moment, which is the same as saying which of these bonds has a greater polarity, which one has a greater difference in electronegativity. Electronegativity is how much does an atom attract shared electrons. So does the bond share the electrons evenly in the middle, or are they pulled to one side or the other? Based on how many protons in the nucleus, those kinds of things, right? So we're interested in who pulls electrons more strongly. But to take this to a molecule as a whole, we need to really sort of think about for the molecule, not only do we have to think about which bond, which atom in the bond, but we have to look at all the bonds in the molecule together. We need to take into account the shape, the geometry of the molecule as well. Okay? Now, a polar molecule, as we know, is one where there is a charge separation, where we have a positive part to the molecule, where the electrons have been pulled away from, and a negative part where the electrons have been pulled to. Just like in a bond, you have a positive end and a negative end. That's where the dipole moment, or the dipole word, comes from. Dipole, two poles, positive pole, negative pole. Okay? So, when we want to talk about polar versus polar bonds, that's distinct from polar molecules. Okay? So we want to think about the difference between a polar bond and a polar molecule. So when I look at the sort of most prototypical polar molecule, water, okay, here is a water molecule. Oxygen, based on where it is on the periodic table, has a much higher electronegativity than hydrogen. Oxygen attracts electrons more strongly. It has more protons in the nucleus. It pulls the electrons more strongly. So there is a net movement of electrons along this bond. On this bond between the oxygen and the hydrogen, the electrons are pulled from the hydrogen towards the oxygen. We can use a little arrow to indicate which way the electrons are moving. We can do this for each bond. Okay? The oxygen is more electronegative than the hydrogens, so there is a movement of electrons from the hydrogen towards the oxygen. In other words, this shared pair of electrons here spends more time around the oxygen. They don't share evenly. We call that a polar bond. There is a dipole moment for this bond. But if I want to think about the water molecule as a whole, I have to think about how do these two arrows interact. Do they add together or do they cancel out? If I have all the arrows in a molecule canceling out, and if the molecule is symmetrically arranged, if the arrows are symmetrically arranged, those arrows will cancel out, and there will be no net movement of electrons. And even though I have polar bonds, I can have a non-polar molecule. In water, these two arrows don't cancel out. A component of their movement of the electrons, a component of this sort of pull on the electrons is canceled out. But they both point up, right? They both point from the hydrogens to the oxygens. Yeah, we'll get there. We'll get there. So in this molecule, the arrows don't quite cancel out. We have a partial negative. Okay, this is a lowercase delta for partial. A partial negative by the oxygen. This is also where the lone pairs are, accentuating this negative, the negative charge up here. And down at the bottom, I have a partial positive. Those are my two poles, a positive end and a negative end. This molecule, water, has a dipole moment. A moment is a measure of a rotational force. And you can measure dipole moments by seeing how these molecules spin in an electric field. Okay? So there's some interesting experiments you can do with that kind of thing. the key for our purposes is that these arrows don't cancel out. Now, if we were to look at another molecule, say like a carbon dioxide molecule. Carbon dioxide, we know, wow, that's really hard to see, isn't it? I'll have to play with that. So, what you want to think about here is for carbon dioxide, let me outline this for you. So, a dipole moment is a measure of rotational force. The more polar a molecule is, the greater its dipole moment. So, here's our carbon, and then we have a double bond to the oxygen over here. Okay? So I'll help outline that a little bit. Oxygen is more electronegative than carbons are. Okay? So this one is, this is our carbon. So which way is the arrow going to point for this bond? The arrow is going to point towards the oxygen. So I have an arrow pointing towards the oxygen, and I have another arrow pointing towards this oxygen. In other words, the electrons around this, for the whole molecule, these two arrows cancel each other out. So there is no net movement of the electrons. And this is a non-polar molecule. Is this a polar bond? Yes, it is. It's a polar bond. The molecule as a whole, however, is non-polar. So when you are looking at a molecule, there are two things you have to think about. I have to think about each bond. I have to draw a little arrow indicating which direction would the electrons be pulled in that bond. Then I have to look at all of the arrows and say, hey, are these arrows canceling each other out, or are they reinforcing each other? Do I have a net arrow, a net movement of electrons, or is that movement of electrons canceled out? And so in this case, those two arrows canceled each other out. We call them non-polar. So polar versus non-polar. The double versus single doesn't really matter that much for determining polarity. All right, now remember there are other situations here. If we had a methane molecule, we have to remember that that's really a three-dimensional structure. That helps a little bit. So a methane molecule is a three-dimensional structure. Okay? Remember when we were talking, we have to keep in mind that we're dealing not just with, flat Lewis structures drawn on a piece of paper, but that we have three-dimensional structures that we have to keep track of. Helps if... no, we'll get there. This is, I'm going to work through this. But... So remember, we have 4 bonds. Okay, no lone pairs. What's the name of this structure? Tetrahedral structure, right? This is our tetrahedral structure. Okay, 109.5s. We need to think about each one of these bonds, and we say, hey, what has greater electronegativity? Carbon or hydrogen? Yeah, carbon is more electronegative than hydrogen. Okay, so we're going to have arrows pointing from each hydrogen towards the carbon. Okay? Now, these arrows, each of them is the same strength, represents the same movement of the electrons. The arrows, I've got 3 pointing at an angle upwards and 1 pointing down. The molecule is symmetric all the way around. those arrows cancel out. Okay? All of them cancel out, because if you look at the angle, when you're dealing with these, what they're called vectors, you have to think about the component of the vector that's up versus the component that's sideways. So all of these sideways ones cancel out, and they all provide a little bit of up to cancel out this down one. Okay? In essence, the key here is to look for symmetry. If you have symmetry around the central atom, then the arrows will in general cancel out. There's a whole set of math you can do that you will learn all about in math analysis, about how you can deal with vectors and stuff like that mathematically. I know a lot of you don't know how to do that. We basically need to look for the symmetry of the molecule. Okay? If you have symmetric arrows all pointing in or all pointing out, doesn't have to, it could be either way, right? These two pointed out, these ones point in. That's irrelevant. It's the symmetry, the fact that the forces on the electrons, whether they're being pulled in one direction or another, is canceling out. That's what gives us a non-polar molecule.
So on the diagram that's on the paper, the two arrows are next, like one's going towards the carbon, and on the same bond, one's coming back.
Right. It's hard on the piece of paper to represent a three-dimensional structure. That's why you have to really think about the actual shape. Because for this polarity stuff, it's the really actual shape that matters, not how you might draw it in a Lewis structure on your piece of paper. So to understand where the more electronegative ones are, you have to keep in mind the trend. Remember that electronegativity is highest at fluorine and lowest at francium. So in general, we don't have to do math calculations. We just have to say, hey, look, this is closer to fluorine or further away from fluorine, and compare the two atoms. Okay? Carbon and hydrogen are actually fairly close in electronegativity. Carbon's a little bit more electronegative, but not a lot. That also helps make the molecule nonpolar. The arrows represent very little pull, not a lot of pull, but they still cancel out because of the symmetry of the molecule. Okay? So, what we're going to do is, I do have a couple of examples I want you to work on. Okay? Now, here's how we're going to do this. I want you to get the model kits. Okay? I want you to build these two molecules. Okay? The ammonium, or ammonia, and this compound that has 3 chlorines and a hydrogen. And then, I thought this was particularly clever, I went to Office Depot and I got little arrow tape flags. So grab one of these arrow tape flags and stick it onto the bonds, okay, so that you can help visualize which way the electrons are going, okay? So each table needs a model kit and just one of the tape flags. It doesn't matter, the color is irrelevant, just look at the arrows, okay? All right, let's look at this. So, you have your NH3, right? You have your NH3. You got your model. Notice that I have 3 bonds, 3 arrows, all going to point towards the nitrogen and slightly up. Right? This doesn't sit flat. This molecule doesn't sit flat. The nitrogen is raised above the hydrogens. All these arrows point slightly up. That means, because there's no bond at the top here, that I have a net movement of electrons towards the nitrogen. I have a polar molecule. Ammonia is actually a fairly polar molecule, okay? One of the high polarity molecules. Now, if I have this same situation, okay, and I'm going to same basic shape, still fundamentally a tetrahedral, right? But in this case, I've got 3 arrows that point out and down, and one that is pointing straight down. There's no up. Okay? Even though the molecule itself is a symmetric molecule, because I have a different atom in here, the carbon, hydrogen with 3 chlorines is also a polar molecule. These are both polar molecules. Yeah. Well, what the arrows, the way I typically draw them, where I put a cross or a plus at the bottom, is that's the side that it becomes positive, and the side with the arrow head is where the negative charge is going. Yep. All right? All right, we are almost done, okay? Tuesday, we're going to put some theoretical underpinnings behind this. We have ideas about where electrons are supposed to be. We have this atomic orbitals. They are not matching where the atoms are in these molecules. That's something we need to address.